So our next speaker is Dr. Veronica Dexheimer. So she will talk about the modular unified solver of the equation of state, the MUSES model. Veronica, if you
can you see my slides?
Yes, we can see your slides, but it's not full screen.
No.
It's a window.
What about now?
Okay, it's full screen now.
Although we can't see your video, which you turned on.
You cannot see me?
Oh, no, sorry. Your video is on. We just can't see it in the room. So you were fine.
Yeah, you're fine. Yeah,
I'm fine. Okay, good.
You shared the slide. It's just that it's probably okay.
Okay. So thank you very much for inviting me. Unfortunately, I couldn't go there. I'm teaching a new class this semester that's taking lots of my time. But please invite me again. I've never been to BNL. I want to be able to go there someday. So I'm going to talk about the MUSES collaboration today, which is an NSF-funded project. It's a cyber infrastructure project, not a physics one. And I'll try to explain to you what its connection to the phase diagram and what we'll be able to provide in terms of the description of the phase diagram. So you don't have to wait until the end. If you want to ask questions, please just jump in. I'll try to answer as much as I can. And if I cannot answer you, I'll just say, sorry, I cannot answer you. Which, by the way, it's pretty normalized. You should all be able to answer, I don't know. If people want to ask questions from the online people, you have to unmute yourself because I won't be able to see your messages. So before we start, for the ones that don't know me, I'm from Kent State University in Ohio. I'll introduce a little bit of our people here. At the Center for Nuclear Research, we have actually a bunch of star people. We have people that you probably know, Declan, Firoz, and Ajambu. From the theory point of view, we have Mike and I. And this is the part of my group that's working on MUSES. It's not everyone. So it's Jeff, which used to be my PhD student. He's also an adjunct professor now here at Kent State. We have Alex, which is a PhD student. Brigitte, which is a postdoc. Mateus, who is also a postdoc. And Johan, who is a graduate student. And a lot of the work I'm going to present comes from them, here from the Kent side, but it's also people from other institutions. So I'm going to start by, I'm going to use the QCD phase diagram as my main motivation here, because that is the main motivation of MUSES. But the phase diagram that I'm going to show you is a little bit different. Usually when you look at QCD phase diagrams, they look like this. I just Google QCD phase diagram, and this is all that came out in the first page. And what all of these have in common, besides, of course, the axis, which usually are temperature and some sort of either density or chemical potential, they all have different phases. So the phase diagram that I'm going to be referring to does not have phases, like all these ones, but instead, they will have regions showing what we know. So the regions that we chose to show come from either first principle or effective theories or experimental data. So I'm going to go a little bit through each of them because they'll be quite important for setting up MUSES. All of these are contained in this preprint, which is a paper which should be, we're in the process of getting accepted to Living Reviews of General Relativity. So I'm not going to be coming back to references as much, but one thing that I wanted to highlight here is that this paper is going to be published as a living review. That means that every couple of years, we're going to revisit it and add more data. So first of all, if I say anything wrong, please write me an email and correct me. And second, if you have new things that you want to share with us, since we're going to be adding to this review every couple of years, please feel free to send me or anyone from the collaboration email and say, add this new paper from STAR. We measured new interesting things that you guys should add up, and we will add up. So what appears in this review, and I'm going to be discussing, is data from heavy ion collisions here. Also more experimental data. I bunch everything that pertains to low energy nuclear physics to this blue region here. Neutron star observations here in pink on the bottom. And then the theory is Carrier effective field theory in gray, lattice QCD in green, and PQCD in pink. And I think the most important thing to see here, and that's, I think, the main punchline of this kind of phase diagram that are trying to make it more popular, is the overlap. If there wouldn't be any overlap, we'd be completely lost here, because we wouldn't be able to use the experiment to verify our theory, or the theory to describe the experiment. So it's great that you have a bunch of overlap, and over time, what we want to do is completely fill this phase diagram with overlaps, so we can be 100% sure of what's going on. And in some regions, at least have a vague idea what's going on. So I have temperature here on the y-axis, density, baryon density normalized by saturation density on the x-axis. And first of all, I wanted to justify why neutron stars is here at all. By the way, I'm an astrophysicist specialized in dense matter. And that's why I'll be talking about neutron stars more than you guys are used to hear. So most neutron star pictures or diagrams that you see are not in scale. So people like to highlight the crust a lot. And the reason for that is that lots of interesting things going on in there. And also everything we see from a star passes by the crust. So the crust is very important for observational properties. But as a dense matter nuclear physicist, I don't really care. What I care about is understanding the matter that it's in the core, which is the most interesting one, in my opinion, which is the one that contains exotic particles. So my postdoc Rajesh put this new diagram together, which I think is interesting because this one is not exactly in scale, but it's more in scale than usual. So the crust is very thin. It's less than 1 kilometer in radius, and a neutron star has about 12 kilometers in radius. So if the crust is about 10% in radius, it's going to be 1/1000 in volume. So the crust is not most of the neutron stars. So most of the neutron star has matter beyond saturation density, so beyond normal nuclear density, and therefore it really belongs in a QCD phase diagram. So going back here, you see neutron star here in the bottom, but there's a lot more than fully evolved neutron stars. By the way, these fully evolved neutron stars have temperatures about 0.1 MeV, so pretty much zero temperature here when you compare to heavy ion collisions with reaching above 100 MeV temperature. And by the way, I send you guys some questions for tonight, which I hope are fun for you guys to go through. But what about young neutron stars? Young neutron stars are hot. They can have temperatures of tens of MeV. So what I'm showing here is a paper from our Polish collaborators, which have made the most realistic explosion of supernova, because they include also the confinement to quark matter, which should be able to reach in such high densities and high temperatures. I'm not going to spend time discussing this phase diagram here, but what I want you to see is you can reach hot temperatures. They kind of normalize by the confinement temperatures here, so it's kind of hard to see. You can also reach high temperatures comparable to ion collisions, low energy ones. But the issue is that most of this hot stuff you're generating, it's not inside the part that's going to become your neutron stars. So this is the dense part. So if you stay here inside this proto-neutron star radius, your entropy per baryon is not as high. So this is going to give you temperatures of tens of MeV. You might ask, what about neutron star mergers? So this is our simulation together with the Frankfurt group. which was the first one to also again allow for the confinement to quark matter. And in this kind of simulation, you get stuff all over. So what we did here is choose just either the hottest part or the densest part. So the hottest part is kind of this ring that you form in neutron star mergers, and eventually becomes the center, where is also the densest part. So it's kind of nice that you combine both here in a merger. And by the way, this combination only happens when you allow for the confinement to quark matter. And when you do that, you can reach, in this diagram here, you can reach about 60 MeV temperature. If you allow more massive stars than what we have been observing to merge, you can get to 80. Some old simulations could get to 100, but in my opinion, that's not very realistic. So we should have a lot of astrophysics filling up this phase diagram. Why we don't? And I think this is very important for you guys to understand that for the time being, we have, by we, I mean like, not me personally, we have been measuring gravitational waves from neutron star mergers, but this is what LIGO measure, here shown on the bottom. So time, so this is the amplitude of gravitational wave, and time is moving towards the right in the horizontal axis. But the thing is, after the actual merger, when the stars touch, it was not observed. And that's because the frequency gets too high, the amplitude gets too small. And this is of the order of 10 to the minus 21. We're talking about a very, very, very small difference in this amplitude. And so the issue is that this was not measured yet, and that's the hot part. So what LIGO measured here, which is shown in the left, was very interesting, because from this tidal deformability, how much the stars deform, we could get information about how big the star is, because the bigger stars deform more, but we didn't get any information about the large temperature part, which is what we would like to be able to put in the phase diagram. So hopefully, very soon, LIGO and Virgo will observe more gravitational waves from neutron star mergers, and you'll be able to fill this up, but not yet. So what can we obtain from astrophysics? We can obtain information from X-ray emission, so not gravitation, but electromagnetic emission from stars. We can infer masses and radii of stars. They have masses between 1 and 2 solar masses. The most massive ones are right at the edge, a little bit above 2 solar masses. We can measure the radii. Just for a few objects, we could measure the radii. Some massive ones, here this data seems double, but because it's 2 different collaborations are reporting here. We also observe the radius of one of the many low mass stars. It's about 12 kilometers. But as I said, we can also extract data for many other properties, including this information from gravitational waves. But that's from astrophysics. But you also have data from, for example, chiral effective field theory, which is a perturbation theory for hadronic matter that allow us to get information until about 2 times saturation density. So that's why the gray region here doesn't go beyond. It does overlap with neutron stars, though, which is great, and it goes a little bit above in temperature. It gives us information about the asymmetry, the isospin asymmetry of matter, which is great because we can obtain that easily from the laboratory. And then you can also get information, experimental information for low energy nuclear physics that includes, for example, low energy heavy ion collision measurements. For example, neutron skin, which again helps us understand isospin asymmetry and heavy nuclei. But it gives us, which is the most important thing, which is information about nuclear physics at saturation. For example, what is saturation density? How bound matter is supposed to be at these densities, how incompressible. And this is all what us astrophysicists use to calibrate our models. Also gives us information about hyperons. And then we have perturbative QCD, which is, from the astrophysics way, the only way to constrain matter at densities, but at very, very, very large densities. the regime that the PQCD people report is above 40 times saturation density. There are ways to extrapolate this to lower densities and obtain information, but it's not exactly the data they provide. And of course, perturbative QCD can apply to any regime of temperature and density, because what's important here is that the energy is very high. So in this case, they can go to next to leading order, which is very interesting that in the zero density, high temperature regime, this goes down to all the way to about twice the confinement temperature. As far as I understand, nobody knows why it can go so low, but it can give us information until around that region. Most of the information here that I say it's information is the equation of state, but in some cases they offer a lot more. For example, in this perturbative QCD case, they can also give us information about the curvature of the confinement line in the crossover regime. I'm not going to be the one here telling you about heavy ion collisions, because I'm pretty sure everyone here knows way more than me about the topic. Just important to highlight that there are lots of information that comes from heavy ion collision. That's why this is such a large region in the phase diagram. I don't know if you guys noticed, but the heavy ion collisions here is kind of fuzzy. And that's because there was a lot of debate and the collaboration trying to determine exactly the shape of this region. But inside this region, we get a lot of information from, for example, particle wheels that allow us to understand the confinement, fluctuation observables, and other things. And then I come to lattice QCD, which gives us a lot of reliable information at zero density, but also allows, if you use Taylor expansions, to expand the right side of the phase diagram here. And the reason this is going so far in density is because we're showing it in units of density, not chemical potential. Otherwise, this will be a little bit different. And this here, in this region, we can get, for example, these derivatives, these higher order derivatives, or like people call susceptibilities in terms of baryon density or chemical potential, strangeness, and charge, or isospin. It also gives us things like partial pressures, although this is assuming that this is an ideal resonance gas. But it gives more information, and one that's my favorite is the one about the critical point, or where the critical point is not. So we know that the critical point is not until mu b is equal to 300 MeV, or from theory that it should be below 132 MeV. And I can try to answer this, talk a little bit more about this if you guys have questions. But I'm just showing a phase diagram in 2 dimensions, and we all know that that's not the case. That's a lot more, or there are more dimensions here, because we have magnetic fields, and they can affect, for example, the confinement line. We also have strangeness, or strange chemical potential. You also have isospin or charge asymmetry, or isospin or asymmetry chemical potentials. So this phase diagram is actually 5-dimensional. And because of that, there's a lot of white space that's not being shown here. The x-axis is also in log scale, and we did this to be able to include PQCD here, but this is also very deceiving because this axis is much larger or longer. So there's a lot of white space here. And how do you fill this up? We have absolutely no option than to add models to fill up this very large portion of white space here. And that's why the MUSES collaboration is going to use first principle theory or effective theory to provide a description of the phase diagram, but it also need models. So my main, so this is my last slide of motivation, which is I thought that I myself, using the CMF model, which is a chiral model of the confinement that I have developed through the years, could describe the phase diagram. I thought I could make 5-dimensional phase diagram, whatever that is, but I never got to it. Because when you add finite temperature and magnetic field together, we found out first, this is very interesting. That's a lot of interesting physics that comes out of it. And second, things get incredibly slow. So each of these curves that I'm showing you is taking about a month to run in one core. Of course, you can use supercomputer to many cores, but it gets to a point that it just becomes impossible for a physicist to do this by him or herself. So what I have here is, I'm showing you the confinement phase transition. So these horizontal lines are looking inside our spinodals. So I'm showing you here different temperatures in different styles of lines and different magnetic fields in different colors. I'm showing you for Havian collisions matter, which is isospin symmetric matter, but with strange chemical potential in blue and black. And then in gray and brown, I'm showing you neutron star matter, which has no strange chemical potential, but it has isospin or charge asymmetry. I just wanted to know that these things are kind of comparable. You cannot say temperature is more important or magnetic field is more important or is isospin and strangeness more important. They are all kind of equivalent in these values that we're studying, which are, by the way, the relevant ones. We're talking about the magnetic field for stars, but also maybe for LHC. Enrique. So we have to include all these features. They are all important, but it's very hard to put all of this to run in a supercomputer. And we can obtain very interesting results out of it that I don't have time to go into. So what do we do? So this is how MUSES came to be, because we had to come together, experimentalists and theorists, and also computer scientists, to try to come up to a way to optimize our codes and also come together to offer more complete descriptions of the QCD phase diagram. So everyone had sort of the same complaint. And then that's how MUSES came together. So the name is Modular Unified Solver of the Equation of State. Modular means that we have to combine all these different theoretical descriptions of first principle theories like EPQCD and lattice QCD, effective theories like carrier effective field theory, and models like the CMF model that I was just talking a little bit about, but other kinds of models. It has to be unified because you have to merge all of this together into something that makes sense, because maybe someone wants to cross this phase diagram diagonally, and that means that we have to combine different things. And we need a lot of help from computer scientists to make our code run by many orders of magnitude faster than what we had. And be able to also stretch to different dimensions that some of our theories or models were not. In my case, I was already had all dimensions. My case was just being super slow. And something that we thought was very important is bring users into MUSES, because we wanted people testing, for example, in hydrodynamical simulations, everything we do in real time, to be able to say exactly what you need and if it's working or not. And I also want to make this open to everyone once it's ready. So these are the initial people that were part of MUSES. So the PIs were Nico Units, which was the main PI in Illinois, where we also had Jackie and George, and Claudia in Houston, and myself in Kent State. And then you have a few senior investigators, including computer scientists, but also physicists, including users. They are testing our things as we produce them, and also external collaborators from around the world. But since then, many people have been added to MUSES, and I'm going to extend the invitation to you, some of you guys, or whoever wants, in a few minutes. So the initial goals of MUSES was to have this cyber infrastructure that would allow people to access our equation of state description online and be able to reproduce all our results, but also stretch them to whatever they wanted to do. So this was not just a repository of equations of state, as some of you by knows, I don't know if you guys are familiar, but for example, in astrophysics, there's this very important repository called Compose. We want to do something different and allow this to be flexible. So what we did was we upgraded existing calculations to modern programming languages. For example, my stuff was all in Fortran 77, which some of you might not even have heard of, but it's a very ancient language. So everything is being written in C++. And you wanted to combine or to allow the user to combine whatever equations of state they wanted. They're going to be combined using smooth transition functions, but in some cases also for Zora phase transitions. And you also want to allow the user to reparameterize some of our modules, not all. So we're going to have some nice interface that's being constructed as we speak. And then people are going to be able to choose what they want to do and either run this in the supercomputers in Illinois or download all this cyber infrastructure and run in their own laptops or in their own, or the supercomputers they have access to. So these were the initial modules of MUSES. We had, was mainly split into parts: the equation of state package and the observables package. So I'll start at the left. The equation of state package had cold nuclear matter, where we have carrier effective field theory. We had QHC model, which is hadronic quark model using the quarkionic prescription. This one might not be able to be delivered because it had lots of issues here if people live in physics. We have the UTK model, which is the only component of MUSES that contain actual nuclei. So this is used, for example, for the crust of neutron stars. Then for heavy ion collisions on the high temperature part, we have our hadron resonance gas module, and also the lattice and extension of lattice to find a chemical potential. And then the effective models will have the CMF that I already discussed with you and a holographic kind of model. Then on the right side, for the observables package, we have for the astrophysics side, the I love Q hydrodeformability and mass radius module. And for heavy ions, we have susceptibilities model, transport, partial pressure, and thermal fits. Over the 2.5 years, so MUSES is halfway, it's 5 years now. We realized that you also have to add a lepton module because you didn't want people treating leptons separately in different modules. This is important for astrophysics. The synthesis model, very important that combines everything together. We also have an interpolator module, which interpolates either to combine things or to allow the user to get interpolator equations of state. But most importantly, what are we releasing? At the time being, we are planning for an alpha release very shortly in May. We're all working round the clock, not sleeping as often as I wanted to be able to finish this in time. This is not going to include all the modules. It's going to include a first set of modules that I'm going to present to you next. It is going to be open source, so everything we're going to release, you're going to be able to do whatever you want to it, as long as you cite us. But it's going to be preliminary. So what we want people is that everyone that's interested to access MUSES and use it and give us their feedback. So what are we going to release right now in May? This is going to be some of the modules that I just discussed with you in those two diagrams. So from lattice, there is going to be two different modules released. The BQS equation of state, which is using an alternative expansion that allows you to go all the way to that green region that I showed you in the beginning of the talk. that extends in μb. For the time being, is going to be 2-dimensional instead of the 4-dimensional we are going to release later. Also, a lattice equational state based on the same alternative expansion mixed with a 2-dimensional, mixed with a critical behavior that's going to give you a fitted critical point, also in 2 dimensions. And then what we refer to as the holographic model, which is an ADS-CFT correspondent based equational state that for the time being will be also 2-dimensional. In this case, in all these cases, meaning temperature and baryon chemical potential. So all of these for the time being, the 3 of these will have 0 μs and μq. So the CMF is quite different. For the time being, we're only going to release the t equal to 0 side of the equational state. So it has 3 different chemical potentials, μb, μq, and μs. But after the alpha release, we're going to extend this to final temperature because the CMF model can also be used to, for example, model heavy ion collisions. So on the low temperature part, we also have Carrier effective field theory, which for the time being is only being released at 0 temperature. Is 2D, meaning μq and μb. And then we have the model that I mentioned, that's the only one that contains nuclei. For the time being, are using at 2D, which is effectively 0 temperature and μb. And what we're also going to release is a combination. We're slowly starting to combine things. So as these things here can be combined, these things here, this equal to 0, can also be combined. And we are also offering composed outputs, which are, again, as I said before, outputs that can be used in this big astrophysics repository. So we are also offering at the time being transport coefficients, such as thermal conductivity that can be calculated for the final temperature modules. And for the low temperature, effectively 0 temperature modules, Climber is our quadruple moment tidal love number, moment of inertia, mass, and radius. So that's what these letters mean, which is our general relativity solver. And also a flavor equilibration module that allows beta equilibrium to be calculated, or near beta equilibrium prefer for the low temperature regime. So although I said that MUSES is a kind of a unified thing, for the time being, what we have is a separate component for final temperature and a 0 temperature. That's going to be our alpha release. And this is my last slide for the broader impact, just a few words. So we have an annual workshop that combines the training camp for young people, and also when you exchange all our ideas that allows MUSES to keep going. And also we're always adding new things every year. We have bi-weekly seminars that are open for the community. So if you guys are interested to attend our seminars, you can go to this webpage of MUSES. I already set it up here to open at the seminar page, but it's lost that you can learn about the collaboration if you go to our webpage. Right now, we're focusing on the alpha release, but right after that's released in May, we're going to plan an online workshop that is going to be for the community to learn what MUSES is providing this alpha release, and also to get information about what you guys want beyond this alpha release. And we're also going to start setting up online tutorial tools that everyone can use if they do not want to attend the workshops, just learn by themselves. This will also be available soon. So that's it. Thank you.
Thank you, Veronica. Any questions? Xin?
Thank you, Veronica. Can you go to slide 19? Thanks for the very nice presentation, a very nice progress. On this figure, I have my understanding is when you call heavy ion matter or versus neutron star matter is basically isospin E0 or neutron kind of rich matter for the neutron star. That's the only difference. It's not a really heavy ion kind of collision. Is that right?
Yeah, so I mean by heavy ion collision matter is matter here with zero net strangeness. So that means that we have to have a finite MUS to be able to reproduce that. We have mu q or mu I equal to 0. That's it.
Yeah, and can you also maybe just let us know what is the roughly region of a realistic heavy ion collision that cover in this diagram, and what will be the neutron kind of star? Now, in the previous pressure versus energy density.
So right now, what we're covering, what MUSES is going to be able to cover, it's a very small portion of the whole thing. So right now we're offering a t equal to 0 prescription here following the UTK model, the Carrier effective field theory, and the CMF model, kind of covering a little bit of this regime. And with lattice and holographic models, we have actually a pretty good chunk here. So if I remember well, the holographic model can go below 100 MeV. So something that covers a good portion of this heavy ion collision region here. So, but once MUSES is complete, we're going to offer, actually this grant period, we're not going to include PQCD description, but within this grant period, we're going to cover a good chunk of the phase diagram. And our idea is in the next grant period extend to also include PQCD description, so it could go even beyond. But right now, we're hoping to cover with lattice QCD, within these different expansion schemes, combining this critical behavior and holography. I assume all this brown chunk here.
Thank you.
Thank you. More questions? Isaac?
Yeah, Veronica, thank you for the really nice talk, and I'm pretty excited to see the release in May. So I have a question on, I don't know if I can remember the slide number, but you mentioned smooth transitioning between different equation of state modules.
Yeah.
In practice, how do you actually accomplish that? Like if you have in the switching region two models that disagree somewhat, how do you reconcile that?
So we wanted to do many different things. So let me tell you first what we're doing at 0 temperature, because that's really my domain of MUSES. So we're offering 3 things right now. A hyperbolic tunge. We are offering first order phase transition if they match, but they also have to match in the right order, right? Because you have to go from the one that has lower pressure to the one that has highest pressure, the given baryon chemical potential. So if they match, we're offering first order. And we're also offering pasta phases between the phase with nuclei and the phase of bulk matter, hadronic matter, and also pasta, if you want, between bulk hadronic matter and quark matter. But that's a 0 temperature where we had more time to work things out. So far for the final temperature, we're offering hyperbolic tunge. And so far, we're not allowing anything to be parameterized. You just get the different models and match them as you want. But later on, we're also going to offer parametrizations. And so you're going to be able to parameterize things yourself. And then things are going to get more complicated to make sure that they match. But right now, we're testing all the matching, and everything that are going to be offered will be physical.
Okay, thank you.
Thank you. More questions?
Can I ask a question?
Yeah, Ronald.
Yeah, so I have a question on slide 23. Yeah, so for these observable packages, are those directly comparable to experimental measurement?
Yes. So we have many users from, for example, the heavy ion collisions, which are running hydrodynamical simulations or transport simulations, and making sure that everything that we are going to offer will be to some extent physical. Of course, as we allow people to parameterize things, some of the parameters that they choose themselves won't be physics, technical, but we're going to have warnings, say, you know, the thing that it shows does not make any sense. Polite warning.
But I have a follow-up question. So that means the user have to supply, say, for example, the initial stage or and the hybridization model, right? Because is that also included in your package?
Ooh, you asked me a question that I don't know the answer for. I'm sorry, I cannot answer that.
That's fine. Yeah.
Yeah, I actually have a follow-up question. Yeah, followed by one. Like, I was also wondering because you mentioned that, as I understand, you mentioned this model has this like input, treated as input. For example, the particle yield, the flow measurement, the HBT, and then with a given state, as Rong said, is a stage, right? The stage you want to look at, then it gave you a output observable. Does it directly give the predicted V2 under this string stage, or it gave us like particles and or it's a momentum we calculated? Like,
So I'm not sure I understand your question. So you are providing
so
things
what
like
would be the output?
Sorry, go ahead.
Sorry, yeah. So my question is like very technical. What would be the output?
So the output is, at the time being, will be some subset of this. So the ones that are going to come out in the alpha release are besides the equation of state, like, you know, energy, pressure, entropy, density, things like that, speed of sound, the obvious things. We're also going to provide transport coefficients. I think everything listed here will be provided, and that will be it for final temperature. The rest is more like zero temperature oriented. So this alpha release is a little bit more zero temperature oriented just because that's what we work more in this first stage, meaning the next stage will work more on the final temperature, a lot more on the final temperature. But this is what comes out besides the equation of state at first.
See, okay.
And then there'll be more things, like, for example, more things that were not there. For example, the partial pressures and some other things that we didn't discuss at first, like the thermal fits will come out at later on.
Okay.
It will be similar to your 2D model, and you have to calculate yourself. It's just a transport that they'll be providing.
Yeah. Okay. Okay. We have questions
I was just
from
going to say, yeah,
Zoom?
we can check.
Anyone has questions? More questions? Okay. We have one. Chunye, please go ahead.
Yeah, very nice talk. I have interest in the 13 slides.
Did you say 13?
Yeah. So do you think we can have ability to study the two-body and the three-body force between the nucleons in heavier clearance based on the Carroll effective field theory?
So we have collaborators that work, which is the group from Houston that does Carroll effective field theory, which is part of MUSES. So what they're focusing on is two things. Is providing equation of state up to about 20 MeV temperature, and also to including strangeness. So they've been working hard, although this is not part of the alpha release. The alpha release will have nucleons and pions, but the idea is to eventually provide Carroll effective field theory, including hyperons, which I think is more interesting for astrophysics or heavy ion collisions. But as far as I understand, the validity of this equation of state is going to continue only until 2 times saturation density. Although, you know, there are more orders being added. For example, there is 3-body forces being included here. As far as I understand, it's very hard to go beyond 2 times saturation density.
Okay, so for the question that what is the upper limit for the this Carroll effective theory calculation for the for the mass number? Like, can it go to the heavy nuclei, or it can only do a good job in the low mass number?
So this calculation does not include nuclei. They include protons, neutrons, and pions, and eventually also include hyperons. Although they fit things to nuclei using specific potentials, the nuclei are not involved. So in our setup here, the only module that includes nuclei is the UTK, which is a kind of statistical model that includes many, many different nuclei and also bulk matter. And these will be included in the alpha release.
Okay, thank you for the answer.
So if you want any trajectory that includes nuclei, you would have to pass by the UTK.
Okay, thank you.
Which right now it's at effectively 0 temperature, but we're going to extend it up to, we are not sure. Really bad answer, right? We're going to extend to up to, we're not sure, but we're not exactly sure how far you go. We're doing some testing here now to move vertically at very low densities and combine UTK, CMF, and lattice QCD to offer that as an alternative equation of state, for example, here. And also we're going to have the HRG model later.
Sure,
So
sure.
the
Thank you.
option going up.
Thank you.
Okay, thank you. Let's thank Veronica again. Very nice talk.